Alright, so in this video I just wanted to go over answers to the sample Redox sample problems 2. Just a quick note, I noticed that there's some problems that are in this set that are the same as in the first set. So some of these might seem redundant. Alright, so which of these factors affect the amount of product formed at the cathode during the electrolysis of molten salts? Alright, so remember, cathode is the place where reduction occurs. So this would be, for example, in the electrolysis of molten salts, this would be the place where the positive metal ions are accepting electrons and getting reduced to the zero charged or metallic form of the metal. All right, so this process here requires electrons to flow into the from the wire into the electrode to allow that process to occur. So anything that increases the electron flow would increase the rate of that reaction. All right, so for that reason, both current and time would matter. All right, current, if you're pumping more electrons through that wire, that's more current. All right, and also time. All right, the longer that you're pumping those electrons through the wire, the more that reaction is going to occur. All right, so as far as charge on the cation, all right, just consider an Na plus ion versus a magnesium plus 2 ion. All right, the sodium Na plus only needs 1 electron to get turned into its metal form, whereas the magnesium requires 2 electrons because it's a plus 2 ion to get turned into the neutral metal. So because of that, you require more electrons if you've got a plus 2 charge than for a plus 1 charge. So the charge on the cation would affect the amount of the product that you could make there. All right. In this next problem right here, it refers to requirements of the standard hydrogen electrode. All right. And remember, when you're doing this, it requires, first of all, in that setup of that standard hydrogen electrode, you need to use platinum. That's the standard for what is used as the electrode. All right, and again, this is an example of an inert electrode. All right, the solution that it's in needs to have 1 molar hydrogen ion concentration. All right, which by the way would be a very acidic solution. All right, if you calculated what the pH of the solution would be here, it would be close to pH of 1. And the last thing was that what was mentioned before is that the pressure of the hydrogen should be 1 atmosphere. All right, and this is a little bit off from what the answer, one of the choices that they give here. So, and the reason for that is typically 1 atmosphere of any gas is considered to be 101.3 kilopascals. All right, but if you look in the IB data booklet and you look at the what they consider to be standard pressure. All right, and here's an example of what I'm talking about. If you just look at, if you look at this, like standard temperature and pressure, notice here that they consider the pressure to be 100 kilopascals. Okay, and by the way, I have a little bit of an issue with the way this is written, because if we were to follow our significant figures rules, exactly, this number right here would only be considered to have 1 significant figure. All right, so that would imply that this could be as much as 200 to 300 kilopascals by the way that they're writing it. All right, if they wanted to be accurate, they should actually maybe put a decimal point after this to indicate some level of significant figures. But anyways, this is what 100 kilopascals is what they use as standard temperature and pressure. And that's why this right here would be considered consistent with what they consider the standard hydrogen electrode to be. All right. In the next problem, they have you take a look at a couple of half reactions with their EMFs, their potentials listed. All right. And so remember, when you're looking at these are written as reduction half reactions. All right. And so if you put these together, remember, only one of these, for a reaction to occur, only one of these would occur as the reduction. All right, the other one would have to occur as the oxidation. All right, so remember, the general rule of thumb is to say that the one that's going to occur as written is going to be the one that is more positive. All right, so if I take a look at these two things and I say, well, which one of these right here is more positive? All right, it's going to be this one. All right, so even though it's negative, all right, by comparison, it's more positive. All right, and remember that the reason it's negative is that all of these are compared to a standard hydrogen electrode. So if you hooked up this half cell to a hydrogen half cell, yes, it would be negative. All right, because a negative number is negative compared to 0. All right, but when you have this, if you hooked up this half cell to this half cell, by comparison, this is the more positive one. All right, so if you take a look at that, what we need to do is we need to take the one that is more negative, all right, and we need to turn that around, because we know that this would actually exist as the oxidation, not as the reduction. And so that's what I've done here, is that I've taken this one right here, and I've taken it and I've turned it around so that it's written as the oxidation. All right, and when that happens, what that does is it turns this into a positive 1.66. So now when you compare, although I haven't written it here, this number to a positive 1.66, all right, the thing that's more positive here would happen exactly as written. All right, so what the question asks for actually is, what is the strongest oxidizing agent? So just recall earlier in the unit we talked about like how to determine these, how these terms are derived at. All right, I use the analogy of a dry towel with a wet body. All right, so obviously we consider the dry towel to be the drying agent. All right, but what's happening to it during that process? It's getting wet. All right, so the reason that it's the drying agent is that in the process of it getting wet, it's causing something else to get dry. All right, and same thing here. In the process of something getting reduced, it causes something else to get oxidized. In the process of something getting oxidized, it's actually supplying the electrons that allow something else to get reduced. All right, so that's a way that you can think about these. So if you look on the left hand side of these reactions, the aluminum is getting oxidized. So since it gets oxidized, you would consider that the reducing agent. All right, and since the lead ion is getting reduced, all right, you would consider that the oxidizing agent. So of all these, when you consider the reactions, you know that the agent is going to be one of the products. So it would not be one of the, it would be one of the reactants. It wouldn't, so these guys could not be the answer because it's not an agent that's in the reaction. All right, so these would be the products of the reaction. All right, so between these two right here, this right here would be the, it's the only oxidizing agent in this particular reaction. So that's the strongest oxidizing agent. So while we're on this topic, let's go ahead and just develop some trends for this particular chart. All right, so if you look at these, remember that the things that are most positive are the things that are most likely to occur as written. All right, and the things that are most negative are the things that are most likely to occur in the opposite reaction or opposite direction as written. All right, so looking at the most positive thing here, this is the most positive thing. All right, so this is the most likely of these reactions to occur. All right, so remember, this is written, these are all written as reductions. All right, so since fluorine is getting reduced here, that means that this right here is acting as an oxidizing agent. All right, so this, since it's the most likely to occur in this entire chart, this right here would be the strongest oxidizing agent. All right, so by comparison, if this is the strongest oxidizing agent, this would be the weakest oxidizing agent. All right, so remember, we could the negative here actually means that it would be that you would turn it around, and that would be very likely to occur. All right, so this reaction right here would most likely occur from right to left. All right, the reverse reaction. All right, so if we write it from right to left, it's actually an oxidation process. All right, so if something very easily gets oxidized, that means it would actually be a reducing agent. All right, so this is going to be your strongest reducing agent right here on this side. All right, and by comparison, this would be your weakest reducing agent on the periodic table, or sorry, in this chart. Okay, so in the next question, we get the solution of silver nitrate being electrolyzed, formulate the half reactions. All right, so the cathode, remember that's where the reduction occurs. All right, so think about the ions that we've got here. We've got silver, Ag plus, all right, but we've also got nitrate, nitrate ions. All right, so what you're going to be looking for in terms of reduction are there going to be metal ions that can get reduced? All right, and again, if you look at the data booklet, all right, so in the data booklet, we know that these are the ones that really don't like to get reduced. All right, these are the things that really like to stay as the ion form. All right, for example, sodium ion. You're not going to have sodium metal sitting in water. But the things on the other side, all right, over here, typically the metal atoms that are happy to exist as metal in water. All right, for example, you can have copper in metal. All right, so if we keep on going down, we see silver is right here. So silver would tend to be the type of ion that would like to get reduced in preference over water. All right, so that's why we could say at the cathode, this reaction right here would occur instead of the reduction of water. All right. At the anode, all right, we're looking for, is there possible that like a negative, generally what you're going to be looking for is, generally you're looking for halogens. Halogens, like halide ions, are the types of things that could possibly get oxidized at the anode. All right. But remember, if it's in water, you've always got that possibility of water getting oxidized. All right, and so since your negative ion here is not a halogen, I would say it's safe to assume that that's not the reaction that's going to occur. It's going to be the oxidation of water that's going to occur. And again, you want to memorize that the half reactions of both the oxidation of water and the reduction of water. And so this is that oxidation of water half reaction. And one thing I want to make stress is to make sure that you always include the state when you're doing all these chemicals. All right, and I actually made a mistake here. I should actually have a parentheses right here with an L beside that. All right, and actually I made two mistakes. This right here should have parentheses with a G beside it to indicate that the oxygen would be a gas. And one thing I've noticed is that in all the answers, they always have the states indicated there. So one bit of advice if you're taking an exam on this, before you turn your paper in, go back through all your final equations and make sure that those states are written. All right, especially on the final things. I mean, if you're doing things to get your just to as scratch work to make up your decision, it's one thing. But in that final answer that's going to be graded, make sure that they are present. So I made a mistake by not putting those in there. All right, and so this last one is one that I actually did in class, but I want to talk about it in two different ways. All right, so the way I described it in class would be kind of in a qualitative sense. All right, so if we just draw a generic redox reaction between metals and metal ions, we would have something like this, where one of the metal ions gets oxidized and one of them gets reduced. All right, so if we take this equation, we put it in a KEQ, all right, it would be this right here. And remember, at standard, we don't include the metal forms. That's why we don't have the zero charge things here. All right, so at standard concentrations, we have 1 molar. All right, so what a negative electrode potential would mean is that the reverse process is likely to occur. So the left process would be likely to occur. So if everything starts at 1 molar and the left process occurs, that means that the concentration of this goes down, which means that's going to be less than 1. And the concentration of this goes up, which means this is going to be more than 1. All right, and so if you pop that into a KEQ expression, the overall KEQ would be less than 1. All right, but what I want to point out is that we could have done the same thing using this reaction right here, where if we just take this, and the N stands for the number of electrons transferred, this is Faraday's constant, and plugging things in to this, we would see that the delta G0 would be positive. All right. So then taking that and using this equation right here and rearranging things using that positive delta G, we would find that the ln of K solving for that would be negative, and if the ln of k is negative, k has to be less than 1.